Hello everyone, welcome back to the second part of numerical errors. In the last lesson we learned about different kind of numerical errors like near truncation error, round off errors or discretization errors. In this lesson we will learn in details of these kind of errors. So first of all, let's talk about round off errors. Round off errors are mainly related to your computer. The more upgraded your computer is, the less the round off error is. So what is round off error actually? So you heard about 32-bit system or 64-bit system. What these 32-bit or 64-bit systems mean actually? It means the biggest word that is available to store data in your computer is 32-bit word or 64-bit word. That means it can represent a number with 32 bits maximum or 64 bits maximum. Numbers are typically stored in one or more words. To understand how this is accomplished, we must first review some material related to number systems. You already know different kind of number systems. For example, the decimal system, the binary system, the octal system, or hexadecimal system. So what these number systems basically mean? For example, in decimal system or base 10 system, the numbers are represented using 10 digits, 0 to 9. In binary system, 2 digits are used, for example 0 and 1. In octal system, 8 digits are used from 0 to 7, and in hexadecimal system we use 16 digits, for example 0 to 9 and then A, B, C, D, E, F. So all of these number systems are useful for different applications. So which system do we use in our computers? That's it. It's a binary system. Binary system is thoroughly used in our computers, all kinds of digital systems. So why this is used? Because it's easy to handle and it's very much useful for digital applications. So to understand a round of error, you need to understand how numbers are stored in a computer. So let's move on. So first of all, consider how the integer numbers are stored in a computer. For example, if you use 16-bit computer, the first bit is used for the sign. That means whether the number is positive or negative. So the first bit is used for this sign bit. The rest of the 15 bits save the binary numbers from 0 to 15 ones. For example, if you have 15 digits, what is the maximum number that you can store using these 15 bits? In binary system, all of these 15 bits should be 1, and that's the highest number that you can store using 15 bits. So if this upper limit is transformed from binary to equivalent decimal, what that number would be? It would be 32,767. So that's the highest number that you can store using a 16-bit computer system. So what does it mean? A number can be positive or negative. So you can store up to 32,767, and in the negative side you can equivalently store up to minus 32,767. But so the range of numbers that you can store using 16-bit computer system is from minus 32,767 to plus 32,767. There are about but there is a loophole here. For example, the zero number is represented twice because there is no difference between positive 0 and negative 0. It's the same number. So we have an extra digit, extra space for an extra number, and that's why we save an extra digit in the negative side, which is minus 32,768. So the range now becomes from minus 32,768 to 32,767. So that's the simplest possible scenario that you can represent positive and negative numbers, where the first bit is used as the sign bit. But you have to know that in computer system, negative numbers are stored using 2's complement method, which we will not be covering in this video or in this course. But you should know that negative numbers are represented using 2's complement, a special method which we will learn in our digital system course. So what is the round of error here? For example, if you want to save a number which is out of this range, the computer cannot save that. So that's the round of error. That's the round of error that the computer introduces whenever you try to save a number which is bigger than this range or out of this range. So that was the case of integer numbers. But how do we save floating point numbers? Integer numbers are very much straightforward to save in a digital system, but floating point numbers have different conditions that we must follow. For example, in computers, floating point numbers are stored in specific format, which is something like this: m and b to the power e. So what are these? M is called the mantissa or significant. B is the base of the number system. For example, if you use a decimal system, the value of B would be 10. And if you use a binary system, the value of B would be 2. So according to the number system, the value of B would change. And E is the exponent. So for example, you want to save a number which is 156.78. So how the computer represents this number in its own system? For example, the number 156.78, it can be represented as 0.15678 into 10 to the power 3. It's a floating point base 10 system. That means we are representing the number with a decimal system. Because why decimal system? Look at the base value, the b value, which is 10, and the exponent is 3. And what is the mantissa? This whole number 0.15678, this is the mantissa. 10 is the base and 3 is the exponent. So that's how we represent a floating point numbers whenever we want to save it in our computer or digital system. So how the computer stores the number or the new representation in its own memory? It represents it something like this. For example, like the integer numbers, the first bit is used as the sign bit, and couple of bits or some bits following the sign bit is used for the signed exponent value, and the rest of the bits are used for mantissa value. So that's how a floating point number is used or saved in the computer memory. First is the sign bit, then some bits are stored or reserved for the exponent value, that means the e value, and the rest of the bits are used for the mantissa value. But there is a problem here. What is the problem? Look at the number 156.78. There could be infinite number of representation using these kind of representation criteria. That means the mantissa could be different. For example, the 156.78, this number could be also used something like 0.15678 into 10 cube, or 0.1.5678 into 10 square, or 15.678 into 10 to the power 1. So all of these representations are valid for these floating point number. So our computer uses which of this system, which of this representation? It has an infinite number of possibilities to save this number. So which representation is used by the computer? The computer has some limitation and some conditions that it must follow to save floating point numbers. So what is that condition? Its condition is something like this. 1 by b is less than or equal m is less than or equal 1. This condition must be fulfilled when you represent a floating point number for the purpose of saving it into the computer memory. For example, if we use a 10-base system, then the value of b would be 10, then the range of m would be 0.1 to 1. But if you use a binary system, m would have a range between 0.5 and 1. So according to the number system, the value of m would change. But since we are using a binary system for our computers, so the range of m should be within this range 0.5 and 1. So that's the criteria the computer must follow to represent a floating point number inside its own memory. So that is the situation, that is the scenario where the round of error comes into account. For example, since the range should be 0.5 and 1, the mantissa value would represent a certain number of digits. For example, look at these examples: 0.078125. So if you want to save it within the computer memory, you should represent it something like 0.78125 into 10 to the power minus 1. So that's the case where you lose a significant number of significant digits whenever you want to save it in the mantissa. Think about it. If the number was allowed to save something like 7.8125 into 10 to the power minus 1, then the mantissa would have scope to save an extra digit in it. So that's the case. That's the place where the round of error comes into account. The computer cannot save some more digits for some more digits inside the memory because of these conditions. It has to follow this condition. So if you want to save these numbers inside your computer memory, those should be represented using these formula. They must follow this criteria to represent the floating point numbers inside the computer memory. So can you find out what should be the proper representations of these numbers whenever the computer wants to use these numbers to save inside its own memory? So that's your homework. I hope all of you should be able to solve this. So I hope you now know what the round of error is, and the round of error is basically due to the computer technology, and it has nothing to do with humans or any other solving criteria. So it's the limitation of our technology. So next, move on to the discretization error. It's a specific kind of error. Discretization involves converting or partitioning variables or continuous attributes to normal attributes, intervals, or variables. So what does this mean actually? To understand the discretization error, you need to know that, for example, you want to save a waveform inside the computer memory. A continuous waveform has infinite number of points within its range, but our computer memory is limited. So how can we save a waveform inside the memory? The computer cannot save infinite numbers. So the computer samples the waveform at specific distances and save those distinct values inside its own memory, so that whenever you draw those distinct values repeatedly, you can find the true shape of the waveform. That's how the computer saves a waveform inside its memory. Let's look at an example. For example, look at this waveform. It's a sinusoidal waveform. It has a specific amplitude and a specific wavelength. That means a specific frequency. So whenever you want to save these waveform, in your computer memory, how do you save that? The computer samples specific points at specific intervals, and those points are saved in the computer memory. So think about this. If you save many discrete points, the repeated whenever you want to redraw the waveform using these discrete points, you can easily reshape the curve in its original form. But if the number of discrete points is very much low, you cannot redraw with those distinct points the true or original shape. And that's where the discretization error is. The more the discrete points are closer to each other, the less the error is. And that's how we define the discretization error. So let's move on to our next error, which is numerically stable error. Numerically stable error is an iterative. Usually whenever you use an iterative scheme in solving a numerical problem, so at each iteration you will have some kind of error, and whenever you repeat those iterations the error will propagate and it will accumulate to a larger value. But whenever this numerical error is constant or it stays at a specific point throughout those many iterations, then we call this error numerically stable error. That means the error is not changing within iterations, or from iteration to iteration it becomes stable. And that's why this type of error is very much complicated to resolve, because you need to reiterate those processes again and again, or you have to remodel your numerical technique. So numerically stable error sometimes removed whenever you restart your program, or you restart the process with different kind of initial values. So that's how you can resolve numerically stable errors. But sometimes it may happen that through iterations to iterations the error grows larger, and sometimes it goes beyond your control, and that is numerically unstable error. So these two different types of errors: when the error is stable, it is numerically stable error, and whenever the error goes beyond the control, then it is called numerically unstable. Now let's look at truncation error. You know that numerical methods use approximations for solving problems. So we use those approximations at every iterations, or sometimes at the beginning of the problem. So these approximations are the true source of truncation error. The errors introduced by these approximations can be understood from the below representation of e to the power x. We know the e to the power x formula can be represented something like this: 1 plus x square by 2 factorial plus x to the power n by n factorial. So this is an infinite series. That means there are an infinite number of terms in these series. But in computer, you cannot use an infinite series to represent a number. So how does the computer uses the e to the power x term? The computer truncates the term after some number of steps. For example, if I want to use the first two terms 1 plus x, the remainder of the terms would be discarded, and that's where the truncation error comes. If you want to use the first three terms, that means 1 plus x square by 2 factorial, and discard the rest of the terms, the numerical truncation error would be smaller than the previous case. So the larger the number of terms you use in your case, the truncation error would be less, and that's where you encounter the truncation error in your problems. For example, you want to calculate e to the power 0.3. Okay, so the x is replaced by 0.3, then the equation would be something like this: 1 plus 0.3 plus 0.3 square by 2 factorial plus dot dot dot. So for up to which term we keep the series. For example, if you want to keep the series up to the second term, that means 1 plus 0.3, the result would be 1.3. But if you want to keep it up to the third term, it would be more accurate than keeping up to second term. And if you want to use up to 10 terms or 20 terms or 100 terms, then numerical accuracy would increase and the truncation error would decrease. So that's where you encounter truncation error. So let's look at the truncation error in more details. So in our last example, the term e to the power 0.3 can be represented with an infinite series. So you cannot just keep all the terms. You cannot keep the infinite number of terms in your calculations. So you have to use a finite number of steps and discard the rest of the terms. For example, if you want to keep up to the fourth term, you represent the summation with a new notation with r bar, then the truncation error would be r minus r bar, because r or e to the power 0.3 is an infinite series. So you are keeping up to the fourth term, so obviously there will be some errors, and that is the truncation error due to truncating the higher terms. So the truncation error is r minus r bar. We can see at another example which is due to the finite divided difference formula. Although we have not covered this formula yet, we will be looking at this formula in our next lecture. So what is this formula actually? Finite divided difference formula. It's a formula to represent numerically any kind of differential terms. For example, dv by dt, it's a differential term. It's the differentiation of v with respect to t. So in numerical analysis, you cannot use these terms. You have to represent this term with an algebraic notation. And that's where the finite divided difference formula comes into play. For example, the term dv by dt, it can be represented using the algebraic notations. In the numerator, you use the vti plus 1 minus vti, and in the denominator you use this term. So we will look into this in more detail in our later lectures, and you will see that the finite divided difference formula is where we discard the higher order terms, and that's where the numerical error comes into play due to the discarding of higher order differential terms. So we will look at that in more details in our later lectures. For now, you just use it as an example. So next it comes into our formulation error. So formulation error, I hope you already guessing what this kind of error would be. This is the error due to the mathematical modeling. So for example, if you want to mathematically model a physical system, you have to take into account many kind of parameters. So whenever you fail to incorporate any important parameter that describes the system more realistically, then the error would increase, and that's the formulation error. You have an error in your formula, you have an error in your mathematical model. So you have to be careful about mathematically modeling a physical problem or any kind of problem. So it's a human error actually, so that does not detract from the adequacy of the solution. So for example, if you remember in lesson 1, we mathematically modeled the physical system, a physical phenomena, which is the mathematical model of a free falling body. If you remember, we used the example whenever you jump out of a plane, then the velocity and the acceleration of the falling body can be mathematically modeled. So we assumed that the air resistance was linearly dependent on the velocity. It was an assumption. but this was not an exactly true formula. For example, the air resistance could be non-linearly dependent on the velocity. So in that case, it might happen that the accuracy of the problem, the accuracy of the solution would increase. So that's where the formulation error comes into account. For simplicity, sometimes we use simple formula, but it's not necessary that that simple formula actually represents the actual situation. Sometimes a complex formula better formulates a physical system, and that's where the formulation error is important. So let's move on to our next type of error, which is data uncertainty. So what's this error actually? It's an actually measurement error. For example, in our parachute model, we used the case scenario that a person jumps from the plane, and we try to mathematically model the velocity and the acceleration of the falling person. So for example, we want to repeat the experiment again and again. What would happen? In some cases, the velocity or the acceleration of the person would be higher than any other case. So the velocity and acceleration are not constant at every point during his fall. If we repeat this experiment, there will be different kind of results. So if you try to mathematically model the parachute falling body, then you see that you have different kinds of results based on the data that you have during the different kind of experiments. So that's where the data uncertainty comes, when you cannot predict what type of data, what the range of the data would be, what the exact value of the data would be. So that's where the data uncertainty comes. So this type of error exhibits both inaccuracy and imprecision. So you already know what is the difference between accuracy and precision. We already covered that in our last lecture. So try to try to remember those differences and similarities between inaccuracy and imprecision. So what is total numerical error? So the numerical errors, so we learned about different kinds of errors, but sometimes not all of those errors could be used in our computer programs. So we only use those type of errors that could be formulated or coded inside our programs. And that's why we use truncation error and round off errors only. So numerically, whenever we try to say what is the total error, we would say it's the summation of truncation error and round off errors. So in general, how do you reduce those errors? We need to account some measures that reduces the errors. For example, if you want to reduce the round of error, your computer program or your computer should be able to save significant number of figures or digits inside your computer memory. The more number of digits you will be able to save inside your computer, the less the round of error would be. And what about the truncation error? In truncation error, you should try to incorporate the maximum number of terms during calculation of finite degree differences or any other terms differences. For example, we used the example of infinite series. It's an example of truncation error where it's very important. So if you need more precision and more accuracy, you may choose a higher number of terms during calculation to reduce the truncation error. We would also see during the calculation, during this numerical solving techniques of new integration formulas or differentiation formulas, we have to use different kinds of step sizes and to calculate our final results. So whenever you decrease those step sizes, the numerical truncation error also decreases. So we will look into this matter in more detail in our later lectures. For now, you just know for a reference. So sometimes there is an inverse relationship between truncation error and round-off errors. So whenever you try to reduce the truncation error, the round-off error goes higher and higher. It becomes more significant, and sometimes when you try to reduce the round-off errors, the truncation error increases. So we have to make some trade-offs between those two different kinds of errors. But know that in our present world, the computers are more advanced than what was in previous era. So the round of errors are never predominant than the truncation errors. So we can actually minimize the round of errors using better hardware systems, like if you have a better memory system with a higher number of bits and higher number of words that can store inside your computer system, then you can reduce the round of errors significantly. So that's how we minimize those round of errors and truncation errors. So for data uncertainty errors, you have to very much careful whenever you mathematically model those physical phenomenon, and if you and you also would be very careful during those mathematically modeling. You need to incorporate many parameters and many variables that are crucial for your problem. So that's how you can reduce the data uncertainty and human errors. So that's for now in our numerical errors. So what did we learn? We learned the different kinds of numerical error definitions like truncation error, round of errors, etc. And also we have known how integers and floating point numbers are represented in our digital systems or digital computers, how those numbers are represented and how truncation error and round of errors comes into play. Also, we learned about discretization error and numerical stable error and the different kinds of sources for truncation errors. So that's for now. So in the next lesson, we will learn about Taylor series. Taylor series is considered one of the most significant subject in numerical methods because we use these Taylor series in most of our future lessons, and also most of the formulas that we use in numerical methods are somehow derived from these Taylor series. So we will learn about this series in our next lecture. Until then, thank you so much for seeing this